Okay, guys, we're live. Hello, guys. So in this video, we're going to be talking about designing chat application. So, Vijay, why don't you get started and ask start the conversation?
Okay. So, but let me first introduce again. Hey guys, I'm Vijay, and yeah, I'm gonna be acting as an interviewer. So here it goes. Okay, so Vijay, can you design a chat application?
Yeah. So let me ask a couple of questions. Like, what will be the purpose of this chat application, and what do people use it for?
Well, these are public chats where people can talk about any topic, including system design, sports, meeting, or anything else.
Okay, sounds good. So, are we supposed to group chat or one-on-one chat?
Let's just say that we are designing a group.
Okay, okay, so we are supporting a group chat, right? So just to help understand the APIs, I might that I might be needing later. So let me draw out what I think the user experience would be look like. So so let's suppose there will be some channels here. Okay. Here will be some channels, and then what we'll have is we'll be having some this group chat, right? So let's say we have 3 users here, right? So okay, let's say we have different users, right? Suppose this is Alice, Bob, and Alice, right? So and there we will be having some timestamp here, right? Timing of the messages, right? In some messages like any topic, right? Okay, and same goes for this one. Suppose conversation goes on this. So something like this, and last pose system design interview, right? So yeah, this will be a normal layout of the user experience which I'm thinking right now, and here we can have some type message here, something like, right? So yeah, this is the normal layout. So and should we be worry about indicating whether the message was read or something?
Well, the wireframe is fine, and don't worry about whether the message was read or not.
Okay. Okay.
We'll
So
take care of that later.
yeah. So yeah. So sounds good. So should we worry about sending images and videos? I know that some chats support permanent storage of the messages and some don't. So I'm going to assume that permanent storage is critically important here for collaboration or something, right?
Yeah, you're right. All those features are important for collaboration. Now, don't worry about images or and videos. Okay. We are
Okay.
interested in storing the message permanently.
Okay. Okay. Yeah. Yeah. Okay. So let me confirm a couple of features. Should we be worry about modifying and deleting our messages, and should we also think about online and offline status, etc.?
No, don't worry about those.
Okay, yeah. Okay, so good. So sounds good. So how many users do we have, and how are they distributed across the world, and how many channels will be there? Like and what's the distribution of the users across the channels, and also what's the maximum number of users that that can be in the channel, and that we expect to be in the channel, right?
So let's suppose that I mean maybe 100 million daily active users.
Okay, okay, yeah, okay. So let me write
we have
it
user
down.
across the whole world. Okay.
Okay,
We have 100 million daily active users. We are assuming that across.
100 million daily active users.
And all the users are across world, but most of the users are in North America.
Okay,
Okay.
okay,
So there are about maybe 100,000 channel. Okay, yeah, we can consider that.
okay,
100,000 channel, and the distribution is a long tail. Where there can be thousands of people in a few people per channel.
okay,
So the maximum number of users is around 5,000.
okay. So yeah, so 5K maximum number of users, right?
Yeah.
Okay. Okay, so let me think about it. Okay, so do we expect bursty send message patterns, and excessive message sizes that could potentially put our systems under pressure or something?
Yes. Since the most users are in North America, so we expect
Okay.
most people to chat about their hobbies at night.
Okay,
We will limit the number of characters to around maybe 50,000 per message, I guess.
okay. 50K per messages, 50K characters, right? Okay, so what's the latency requirement for sending the message, and how quickly do we expect to deliver the message to all the users? And I would expect it that it should be low for chat to be more interactive, and also what about the loading time of messages for a given channel?
Yeah, that's right. Let's target less than 100 milliseconds from one user to another,
Okay,
and for message loading time should be around 200 milliseconds.
okay, so
Okay. For
200 millisecond. Okay, yeah,
Yeah.
sounds good. Okay, so this might be obvious, but I'm assuming we have to deliver exactly what the original user sends, right? So the API to send a message should be available. Otherwise, it will be frustrating experience. And okay, so the chat messages should be durable, since people may look at the history, right?
Yeah, that's right.
Yeah. So let me just define API, and based on the requirements, I'm thinking of the following APIs. Okay, so let me see. Okay, so I'm thinking of like there should be uh, there will be a send message API endpoint where it takes user ID, message, and channel ID to send message to, right? Okay, channel ID, which returns the status whether the message have been sent or not, right? And then we can have read messages API endpoint, right, where it takes user ID, channel ID, and offset, right, so that we include it will be useful for pagination and all, right? so it will return message. Okay. Then I'm thinking of another endpoint that like receive message, which will take channel ID and message, right?
Yeah.
So for send message, a user sends a message to a particular user, right? And it will so for send message, the user sends a message to a particular channel, right?
Yeah.
Our user ID and then channel ID, right? And it will return whether it went through or not, which is a status basically, right?
Yeah.
Okay, so and for read messages, we will retrieve a list of messages back for a channel ID, right? For a channel ID, and since the user can scroll up for historical messages, I will assume we need pagination with an offset, right? So the paginated page size will be fixed, and so the client doesn't need to pass it, right? Okay, so and for receive message, it is a callback function upon receiving a message, right? From other users. Okay. Yeah. So the message consists of a written text, the author, and the timestamp when the user sent it, right? So let me just go through and define high level diagram for it, right? So that like now that I have designed the APIs, right? So I'm thinking of a high level diagrams that to put all the API calls and the services together. So for this I'm going to assume we need web sockets to send and receive real-time chat messages, right? So and also I'll add a queue in anticipation of handling high write throughput, since it's a chat application, and we will dig into them more and modify them if my assumptions are wrong, right? So let me just go through and design a simple high level design. Okay, shrink it a bit. Okay. Okay. So we will have a user, right? User, couple of users, chat server will have a user, right? And we'll have a chat server, right? And then we'll have a message queue. Okay. Okay. So for the basic aspect, like there will be a call from it will user will send a message to a chat server,
Yeah.
right? And then user can receive a message from chat server, right? And then also user can read message, right? So let me put some text over here. Send message, right? And then user can receive message. Let's just call it MS. And also user can read message. Okay, and then chat server will be talking to message queue, right? And then we'll have a couple of backend services such as chat processor, right? And we will be having chat storage as well, right? Chat processor and chat storage. Okay, then we will we can have a multiple of this, right? Also we can have many users. um, um, they can have, you know, two-way communication here. Let me see if only one. So user can have two-way communication here, right? Okay. Okay, so chat server get messages from chat processor, right? This yeah. So we can have, you know, multiple chat server, right? And then they each of them, you know, talks to chat processor, right? And this backend services, right? Yeah. So yeah. Let me see. Okay. Okay, so here's my initial take on these schemas, right? Um, so for the message queue, you know, schema for the message queue, I'm thinking like there it can have, you know, user ID, channel ID, message, author, and timestamp, right? We will be storing all of them, right? User ID, channel ID, message, author, timestamp, right? And for this will be for message queue, right? Then we then for chat storage, we can have a message table for it, and we can store channel ID, right? Timestamp, message, author, right? And also for chat storage, this can have, for channel table it will have channel ID and name. Okay. Okay, so let me just quickly summarize the end-to-end flow. So when the user initially logs into the chat application, right? Logs into the chat application, the user calls read the user calls read messages for a particular default channel from the chat server, right? And the server will retrieve the list of messages from the chat storage, filtering for the latest messages for the channel ID of interest, right? And when the user sends a message, the message gets passed to the chat server, right? And then and it gets forwarded into the message queue, right? Chat server, and then gets forwarded into the message queue, right? And then and then the chat processor will pull from the chat processor, and the chat server will pull from the chat processor and look up which chat servers to forward the messages to, and eventually the recipients will receive the messages through the WebSocket callback function, right? Receive message. And then for maintaining the chat server, WebSocket connection lookup is something we can discuss further later if we have time, right? Okay, yeah.
So, okay. So, looks fine to me, but I have one more question. I don't know if you're going to like it or not, but I'm going to ask you, what do you like and not like about your design?
Okay. So there are couple of places I want to consider alternatives and trade-offs, and some aspects I would like to go a little bit deeper to. So here are topics that I can think of so far, right? So one I can think of is concurrency of a channel, and then second, like storage solution, and also efficiency in querying for the latest messages, right? And real-time data, and also like scaling for write throughput. So is there one that you would like me to talk about?
No. Feel free to focus on whichever one you think is important. Okay.
Okay, so you can actually for the okay. So let me just discuss about the concurrency of a channel, right? So you can think of a channel as a shared resource, right? And multiple write to the same channel resource. Luckily, messages don't affect each other, right? So we still have we still have concurrency problem with two users write simultaneously concerning the ordering of the messages. Okay, so right, so like so suppose okay, let me just make a copy of it. Okay, so suppose okay, yeah. So I mean, while two users write simultaneously, it may be the case that the order of the messages may arrive, or delay a bit, or the order might get disturbed, right? So so that's something to consider, and consider more about it, right? And if we right, so and option one that so if we suppose for example, if we put A's like suppose there are two users, like user A and user B, right? So if we put A's message before B's message, it will be inconsistent when B reloads their dashboard, since B saw their message before A's message when they typed want to join or something, right? Yeah. So I think in order to solve this problem, I have a couple of options to list. The first option, the first approach that I'm thinking right now is let me get myself a room here. Okay. Okay. So option one that I have right first is the store the ordering per user, right? So what we can do is we can store a version number per chat message for each user, and the client side will generate the versions based on the client side ordering, right? So now that sounds good in theory, but there can be multiple sessions for a given user in practice, which brings up the which brings up the original concurrency problem which we had, right? And if you store it per session, it's unclear which session is the source of truth, right? So and also on top of all that, it is storage intensive to store the versioning numbers per user, right?
Yeah.
Does that make sense?
Yeah, it does.
Okay. So another approach to solve this problem is optimistic lock, right? So optimistic locking is unlikely to be good solution, but it's worth going through, right? So since it's a concurrency problem, right? So if a user or if a writer hits the database first, the second writer will fail, right? And the server will ask the client to retry again. Actually the advantage is the consistency in the ordering per user, right? And but the disadvantage is a highly concurrent environment. The number of queries, the number of retries will cause it to be almost unusable for a chat application, right? So another solution for this can be to use pessimistic lock, right? So every time someone writes a message, it requires a lock for the channel, and everyone else can write a message, right? Yeah. So but this will be the worst chat application there is. So no, I mean this option 3 is not a good solution to be considered, right? So let me think of the another approach. I think we can use a timestamp as a source of truth, right? What do you think about it?
Yeah, we can use that.
Okay, yeah. So I mean, like for in options 1 to 3, where we are attempting to have a consistent experience per user. What if we relax that and assume a hard refresh with a different ordering with a different ordering is acceptable, right? So and there will be many messages in a highly concurrent environment, so it's unlikely the user will notice the ordering inconsistency, and also the concurrent messages don't have relationships with each other since the users are typing simultaneously, right? So and also for those reasons, I will assume ordering inconsistency in a highly concurrent environment is acceptable. Okay, so with that user experience in mind, we will use the server generated timestamp as a source of truth, and we don't want a client timestamp because it can be tampered with, right? And there can be clock skew on the client side, right? So there can be clock skew on this and on the server side too, but depending on which server generated the timestamp, but we are in control, right? So we can always synchronize the clocks periodically to bring the clocks close together. Okay, so we in this case we do want to be careful about the granular details of the timestamps, and if the granular detail is too coarse, like in a minute, we can tell which messages came first within the minute, right? So for now I will use milliseconds. If there are conflicts within a milliseconds, we're okay with either ordering, since it's very unlikely there will be meaningful ordering within a millisecond, right?
Yeah.
So that sounds good, but I'm thinking of another approach to solve this problem. let's call it option 5, and I think we can use, you know, auto increment id. So this possible approach is to, you know, use a monotonically, you know, increasing unique id generator like that we use in Snowflake, right? That way we don't need to worry about the conflict of timestamps. However, you know, a distributed id generator is roughly ordered, right? So in the worst case scenario, the id might sort it in a certain way that is, you know, inconsistent with the timestamp attached to the message, right? So for, you know, assuming we don't need a strong consistency for each user, options 4 and options 5 are, you know, the reasonable solutions, right? So and also for this session, I'd like to keep it simple with option 4, since generating a timestamp is more straightforward than you know, having a dependency on a you know, distributed id generator, right? So we can just go with option 4, right?
Okay, yeah, that's fine, and I've seen both in production.
Yeah. Okay.
But I agree with keeping it simple for now. So can you go a little bit deeper into your storage here?
Okay, yeah, sure. So let's okay, yeah. So let's talk about the database solution I would choose, right? So database solution, right? So let's you know, first let me assume the write to read ratio is high, because the read query only happens when the user logs in or visits a channel to retrieve the latest messages, right? Once the user is in the channel, the user is expected to write multiple messages, right? So option 1 that I'm thinking of is we can easily solve this problem with standard relational database management system. Okay, so standard RDBMS. Okay, so let's consider like RDBMS storage like PostgreSQL, right? Generally RDBMS is a great for transactions and is well understood and supported, right?
Yeah.
So but the disadvantage is that RDBMS is better for reading because it uses B-tree instead of LSM, right? So that right, and also so in this in our scenario, like in the case of chat application, which is, you know, write heavy, so B-tree is usually not a fit for this solution, right?
Yeah.
So also the way we retrieve the data is by a list of recent messages, right? So given the schema above, right, let me just, you know, write a schema, right? So for this schema, right, chat storage, so you know, given this schema, retrieving messages from a channel ID won't have good disk locality, since you know, data is stored on disk by row and messages, right? For and messages for a channel will be stored in, you know, multiple rows, right? So yeah, that might not be a good solution, right? But I'm actually thinking about option 2 for this problem, for our storage solution, right? So option 2 that I'm thinking right now is to use a white column leader follower, right? Where you know, I know a white column store is, you know, generally better for write throughput due to the LSM based append only property. There's a better disk locality since the system stores the messages in a column family for channel ID, right? So as far as replication goes, I can choose a leader follower like HBase, and in the case of failure, I can elect a new leader, which may result in temporary unavailability. And however, we will have a stronger consistency since writes are done on the leader, right?
Yeah.
Okay, so let me think of another solution for it. We can use white column leaderless as well, right? So like another white column solution that we can consider is white column leaderless replication is tool like Cassandra, like, right? So with leaderless, we need to worry about conflicts, all right. So imagine two users modify or delete the same messages simultaneously, right? It will be very unclear how to resolve it. However, the leaderless replication has better availability, since we need to worry about the leader going down in a leader forward application schema, right?
Yeah.
Okay, so for this scenario, I think RDBMS sounds like a clear no, unless we are operating on a small scale, right? And given we have a tenth of billions of users, right? I would like to consider the right performance, right? And ultimately, I would favor option 3 because of better availability, right?
Yeah.
Okay, so and also users can't modify and delete messages in our requirement assumptions, so conflicts aren't an issue yet. But in the future, when multiple sessions can modify the same messages, then we will need to basically worry about the complexity of conflicts, right? Okay, so now I would like to focus a little bit on the architecture, since the end-to-end delivery is very time sensitive, right? So let me just lay out the architecture for chat architecture, right? So for chat architecture, I'm thinking of like simultaneous broadcast, persist and persist to disk, right? So simultaneous broadcast and persist to disk. Okay, so let me just draw some architecture diagram here. Okay, we don't really need them right now. Okay. Okay, so suppose we have a user, right? We will have a chat server, chat application, chat server, and can get rid of this, and then we can add storage solution and queue. Okay, so we'll have user sends message to chat server, right? We have chat notification server, and okay, so the user flows looks like something like this. Okay, so user sends message, right? It gets into message queue, and then message gets stored into chat storage. Let me write this. message queue, chat storage, right? And message queue pushed on to chat notification, and chat server fetches it, right, and push it to the user notification. Okay, so in this case the messages gets fanned out to both the chat storage, right, chat storage and chat notification when removed from the queue, right?
Yeah.
So in this case the latency will be lower, since since we don't need to wait for the messages to go to the disk first, right?
Yeah.
So but however when the storage cannot persist, the system will the system will notify a message that that never made it to the database, right? So leading which basically leads to inconsistency, right? So for this problem I can think of the solution that we can write to disk first, right, and then broadcast, right?
Yeah.
So what we can have is we can have the same stuff here, same architecture here, but instead of this one, we can just write it to disk first and then broadcast it later, right?
Yeah.
This is okay. So in this architecture, a message is like written to disk first, right, before notifying the user, and then so the advantage is the modified message is guaranteed to be durably, right, durably stored on chat storage, right? And if the message fails to persist or to disk, the system will not broadcast the message to the recipients, and however the end-to-end latency will suffer because it adds the disk latency, right? So yeah, latency can be a bottleneck here, right? So given we need a very low latency application, I would still prefer option 1 and monitor for chat storage failure, right?
Yeah.
Chat we can monitor for chat storage failure rate, and then retry the failures and hope they go through, right? And if failures become a problem, we should investigate to reduce it, and so for now we'll assume a rare error event leading to an inconsistent notified message is acceptable, right? So let's just focus on the performance of the read query. Okay, the solution that I'm thinking of is for the performance of read queries, we can do a full table scan, right? So let's suppose the schema is this, right?
Okay.
Let's suppose the schema is this. What we can do is we will need to filter for all the messages in the channel ID, sorted by timestamp, right? Sorted by timestamp, and return the paginated list of messages, right? The advantage is we don't need to worry about indexing on write, and however the read query will be poor without the index, right? So let me lay out option 2 for this one. Which is we can do compound indexing, right? We can index the table by channel ID, right? We can index the table by channel ID and timestamp, and it will be indexed by like channel ID, right, and timestamp, right, both. Okay, so for each channel ID, the timestamps are sorted already, right? So retrieving the latest end messages will be efficient. but the downside to this approach is the write will be slower with an index, right? So for this problem to solve, we can do, we can read cache, right? We can use caching, right? So in order to increase the read performance, we can use read cache, right? So given the read latency requirement of 200 millisecond, right? 200 millisecond, 200 millisecond, and the read to write ratio is low. I'm not sure if it's worth dealing with the cache complexity. For every message we write, if we do a write around with a read through cache, the writes will frequently invalidate the cache, right? So if we write to the cache first with the write back cache, we risk losing the messages before persisting to the disk, right? Does that make sense?
Yeah.
Okay, so I would choose option 2, since the read is much more performant. The write is slightly slower, but we're already notifying the users before disk, right? So the disk latency isn't an issue. Okay, so
yeah. So you mentioned about the WebSocket, right?
yeah.
So are there other alternatives?
Yeah, sure. I think I have a actually there are a couple of options that I'm thinking right now. So let me just go ahead and list them out. Okay. Okay. So the option that I'm thinking of is, we can use sort polling, right? So what we can do is right, we can do option 2, we can do short polling, right? So so what happens in short polling is the client will periodically call the backend for the latest messages, right? The advantage is simplicity, since a simple HTTP would work at the cost of many unnecessary calls if there's no update, right? So this is a good option, considering if we are going for simple solution, right? The second solution that I'm thinking right now is we can use long polling, right? So where the client will call the server and keep the connection open until a new message is available, right? So if there's no response after some time in long polling, it will time out and require a client retry, right? And the server also has to deal with the complexity to keep the connection open. Okay. Okay, yeah. So option 3 is just simply a WebSocket, right? So the advantage of a WebSocket is to keep the connection on both sides, right? So the advantage is if a new message comes, the message is forwarded to the client right away. The downside is the complexity of maintaining and building the WebSocket infrastructure. Okay, so for the solution, for considering this couple of options, I think WebSocket is gaining a lot of popularity these days, and given the inefficiency of sort and long polling, we will just go with WebSocket, right?
Yeah, sounds good. Well, that sounds pretty straightforward. But can you go over how you would scale up your database?
Yeah, sure. So okay, so sure. I mean, I'm going to assume by scale up you mean whether the database can handle the write load, right?
Yeah.
So should I do some back of the envelope math to see how many machines are needed?
No. Let's just assume we need multiple starts. And what is your studying strategy on that?
Okay, let me think of a couple of options. I think we can just for option one, we can just we can sort it by channel, right? So sort by channel ID, right? So in this solution we will start by channel ID using consistent hashing. The advantage here is to retrieve a list of messages for a channel ID, right? And starting by channel ID will be very efficient since they are all in the same sort, right? So but the disadvantages are hotspots, right? So if there is a lot of activity for a channel ID, that sort will be a hotspot, right? And also popular channels will lead to significantly more messages too. So I think we can we can find another solution for it, and and I'm thinking of a different solution is that we can start by timestamp bucket, right? So sharding by timestamp bucket means having buckets of time ranges. So there will be a bucket for the current time where all the channels write to. Okay, so does that make sense so far? Okay, so the advantage of doing so, the advantage of starting by timestamp is that you can fetch all the latest messages for all the channels in the same shard, right? And sharding by timestamp will lead to a hotspot since all writes for all channels are written to the same shard. Okay, so this can lead to a this can lead to a more problematic scenario. So I think we can go for a better option, and let's just shard it by channel ID as well as timestamp bucket. Okay, so we can do sharding by channel ID and timestamp bucket. Okay, so instead we can instead of choosing option 1 or option 2, we can just shard it by channel ID and timestamp bucket. But and the advantage of doing so is the ability to fetch the latest data for channel effectively, right? So instead of having a shard that handles all messages for all channels, the schema will distribute channels across shards, right? And another advantage is you're able to fetch a channel's recent messages efficiently. But the downside and the disadvantage is that there's still a potential hotspot if a channel has unusually high activity, right? And also the system will create a new time shards consistently. So if a channel is inactive, you may need to hit multiple shards before hitting the shard with the latest messages, right? Yeah, so using using this approach, I think we can this approach might solve our problem, right? So let me just think of option 4. Like we can do another approach there by sharding by channel ID and random, right? So like in this design, I'll predefine a list of shards for a channel ID. Upon receiving a write request, I will randomly pick a server to write to. On read, I will have to scatter gather from all the shards for that particular channel ID, right? Yeah. Okay, so the advantage of doing so is there won't be a hot shard due to the latest timestamp. However, the disadvantage is that the read will be less efficient since we need to scatter gather, right? So if we add more nodes, the scatter will become even bigger. So for database scaling, I think option 1 and option 2 are probably not sharded enough and will cause storage and hotspot issues down to the line. Option 3 is perhaps my choice, and I just need to be aware of aware of a super popular channel and potentially handle it differently than I do for not so popular channel, right? So and option 4 is an option if we absolutely can't handle the write throughput, and but in practice super high QPS super high QPS is unlikely, and imagine people are writing at 10,000 QPS, right? uh, 10,000 query per second. So who is going to be able to read any messages, right?
Yeah.
So yeah.
Okay, so yeah, it was a good one. I think you covered all the important topics.
Yeah.
I don't think I need to ask any other questions. Okay, yeah. Thanks for your time, Madhuri.
Okay. Yeah. Thank you, Vijay. So thank you guys for watching, and we'll see you in the next video, right?